Oh, right. Our today's speaker is Reza Mohammadpour, now in Uppsala, and the title is SRB measures for partial hyperbolic systems.
Okay, thank you very much, Miha, and also thank you very much for the invitation. I'm so happy to be there virtually. Before I start my talk, let me mention, feel free to stop me, ask questions during of the talk. Today I'm going to talk about the SRB measure for partial hyperbolic system. Let me mention general setting for this talk. T be a homomorphism on compact manifold of the X, and I usually use of the for the Lebesgue measure, normalize the Lebesgue measure, means that Lebesgue X is equal to 1, mx, the space of all probability, Borel probability measure on compact manifold of the X, and mxt, the space of the alt-invariant Borel probability measure on compact manifold of the X, which is non-empty and compact with respect to weak star topology. So there are the general setting for this talk. For any point of the X belong to compact manifold of the X, we denote by Px set of the accumulation point of the sequence of the empirical probabilities. I mean, this sequence gamma n x, which is 1/n sigma from J0 till n-1 delta Dirac of the TJX, where delta y is a Dirac delta of the probability measure supported at y. In other words, Px is the set of the measure which there exists of subsequence nj, the gamma njx as j goes to infinity is equal to mu. And it's easy to see that this set is always a subset of, the T-invariant Borel probability measure. As I mentioned, 0.1 is called empirical probability. And this set is a compact with respect to weak star topology. That is why this set is always non-empty. Now I'm going to introduce observable mesh. This is the main definition of this talk, and it's a very important definition. And categorize and inherit introduced the observable mesh. A probability measure is observable or physical like if for any epsilon greater 0, the set beta epsilon mu, which is set of the point, the distance of the PWX and mu is a smaller epsilon. Distance, in the space of the, in weak star topology sense, has a positive Lebesgue measure. And we call beta epsilon mu the epsilon of basin of the epsilon attraction of the mu. And we denote by O the set of the all observable measure. And category the nearest to show that the set of the observable measure is always non-empty and compact with respect to weak star topology. So for a system, an observable measure always exists. And as categories and inherit to show the set of the observable measure is compact with respect to weak star topology. I hope this definition is clear for everyone. If it's not clear, please let me know. I can explain. Okay, and a probability measure is called physical if the set of the X, PW, and the limit of the PW exists and equal to mu. And this set, which is called basin of the attraction of the mu, has a positive Lebesgue measure. And we denote by PPA the set of the physical measure. So difference between of the physical measure and observable measure as a follow. The limit, this limit, in case of the physical measure should be exist, then the basin has a positive Lebesgue measure. But in case of the observable measure, we can talk about the accumulation point and a measure around of the accumulation point. Let me mention this remark: a physical measure is not necessarily ergodic. There is a nice example by these guys. They gave their example is a one-time one-time map, and for some parameter physical measure is not ergodic. And it's easy to see that any physical measure is observable or physical like measure, but other side is not true. I mean, an observable measure is not necessarily physical measure. So in general, for a system, we know that an observable measure always exists, but not a physical measure. Look at this example. Let G be the transitive pseudo-anisotropy diffeomorphism. By Sinai theorem, there exists a SRB measure which is physical. Now consider the product of the map G times identity. To be more precise, consider this function f from T3 to itself, pseudo map, I mean in three-dimensional torus, which define it fxy goes to, I mean, identity times map G. And one can see that the sequence of the empirical probability measure converges always to Dirac point times the measure mu. The mu is the, I mean, physical SRB measure, which is supported, I mean, one-dimensional unstable manifold injected the tutor. I mean, point times a two-dimensional torus. And measure of the mu x are mutually singular because of the we consider different value of the x on circle. And it's easy to see that based of the attraction of the b mu x, this is the b mu, I mean, mu x is this, as a zero Lebesgue measure in the ambient manifold. So none of the probability mu x is a physical for f. And as an exercise, one can show that in fact the set of the observable measure is equal to set of the, I mean, all mu x. So for this simple system, there's no physical measure, but observable measure exists as categories in Harish to prove. So that was the example. Given a continuous map of the A from X to invertible matrices, and we consider A and X equal to A, T n minus 1, T over n minus 1, till AX, the pair of the TA is called a linear cocycle, which induces a skew product. XV goes to TNX, ANXV. And if T is the invertible, then F, so is F. Moreover, we can define of the inverse of the F, as you see, by A power minus NX is equal to inverse AT minus X, so till inverse of the A at the point T minus X. So that was a definition of the linear cocycle. So let us see a simple example of the linear cocycle. The simple example is as follows. The linear cocycle generated by a diffeomorphism of the map T on closed Riemannian manifold M to itself, and a family map of the AX, which is the derivative at point X, at tangent space at point X to tangent space at point Tx. I mean, this cocycle I call it derivative cocycle. So that was the simple example of the linear cocycle. Let F be the C1 diffeomorphism on a smooth manifold M to itself. I mean, I usually use of the notation of the cocycle for, I mean, the derivative of the function. Given X belongs to manifold and the V is a vector and belongs to tangent space, the Lyapunov exponent, the lim 1 over n log norm A and X as n goes to plus minus infinity. And we have a classic result of the oscillator to say that, I mean, if I mean, let F preserve an invariant probability measure mu, there exists a measurable function of the lambda I, which call it the Lyapunov exponent, and a DF invariant splitting. I mean, this is splitting with the, I mean, lambda xv is equal to lambda I xi for mu almost every point, and every v belongs to oscillatic space. Moreover, if mu is ergodic, then the Lyapunov exponent and dimension of the oscillatic space are constant, mu almost everywhere. So that was a classic results by Osseledek. We denote by R, a mass color R, the regular set, which is the set of the point which the Lyapunov exponent are defined. Because by Osseledek theorem, we know that the Lyapunov exponent exists for mu almost every point. So I denoted regular set by R. Then we have a famous result of the Pessin to say that if X belongs to regular set of the R and has at least one positive Lyapunov exponent, then there is a small unstable disk gamma u tangent to positive part. I mean, tangent to oscillating space where you have a positive Lyapunov exponent. But it seems that we need at least one positive Lyapunov exponent, such that for all y belong to unstable disk, lim supremum 1 over n log distance of the inverse of the, I mean, f power minus nx and f power minus 1 is smaller than 0 as n goes to infinity. And the gamma u is called unstable disk or Pessin unstable disk of the X belongs to regular set. And a stable disk can be defined similarly with at least one negative Lyapunov exponent. So the idea as follows: when you have a uniformly hyperbolic or unsolved diffeomorphism, one can use of the classic result to existence of the stable and unstable manifold, but one can extend it to more general class. The class is that you need, if you have at least one positive Lyapunov exponent or one negative Lyapunov exponent, you can define of the unstable disk. Let M be the C1 diffeomorphism compact Riemannian manifold, and we say that a Borel invariant measure is a hyperbolic if you have a non-zero Lyapunov exponent. As I find it here. And sometimes I use this notation for Lyapunov exponent because by Osseledek, you define Lyapunov exponent corresponding to Osseledek space. But here I consider all Lyapunov exponent here counted by multiplicity. For instance, if you have your Osseledek space is the dimension 2, you have a 2 Lyapunov exponent might be equal. There we go. And that's the Lyapunov spectrum of the co-cycle with respect to some invariant mesh. And the lambda, defined by Osseledek, and the chi, the Lyapunov exponent, which counted by multiplicity. Multiplicity, the dimension of the Osseledek space. Assume that X belongs to regular set of the R, has at least one positive Lyapunov exponent. So by Pessin theorem, we know that there exists unstable disk. So we define unstable manifold of X as follows: takes inverse of this function, n's inverse, then acted in the gamma u unstable disk, then take image of the n. Then finally we take union of the for all n positive. And that's the definition of the unstable manifold. And a measurable partition of the P of the set X. What I mean with measurable partition in the sense of the, Rocklin theorem. Rocklin theorem, they say that a Borel probability measure has a distinguishing with respect to some measurable partition. And that's a measurable partition. A measurable partition of the P of the set of the X is said to be subordinate to unstable manifold if F has at least one positive Lyapunov exponent, mu almost everywhere, and for mu almost every X, the element of that measurable partition contain X is a subset of the unstable manifold. This is really important. It's been the element of the measurable partition should be contained of, is contained of a piece of the unstable manifold. So that's the definition of the subordinate to unstable manifold. And let's define of the SRB measure. A a probability hyperbolic measure is called a Sinai-Royal-Bowen SRB measure if for any measurable partition of the P subordinate to an unstable manifold, the conditional measure of the mu with respect to a measurable, that measurable partition which is subordinate of the mu are absolutely continuous with respect to conditional measure of the Lebesgue, and we denote by SRB, the set of the SRB measure. Again, a SRB measure might not exist or for a system, but observable measure always exists. Every ergodic SRB measure is a physical measure that follows from the pacing theory. And we have a long-standing conjecture by Viana. The conjecture that states that if a smooth map F has an only non-zero Lyapunov exponent at the Lebesgue almost every point, then F preserve an SRB measure.
Does smooth mean C1 or better?
You mean conjecture?
Conjecture, yeah. C1 or C1 plus epsilon at least? Or
Well, yeah, I think,
what's expectation?
Expectation is C1 plus epsilon.
Mm-hmm.
And this conjecture recently proved for surface diffeomorphism, C infinity surface diffeomorphism by David Borger. Some months ago, 2-3 months ago. For surface diffeomorphism, it means that in dimension 2, if you have a positive Lebesgue, positive Lyapunov exponent for set of a positive Lebesgue, then there exists SRB measure. Are there question or comment? Yeah, feel free to ask any question, stop me, correct me if I'm wrong.
I have a question.
Sure.
So here, so the subordinate to unstable manifolds is considered. If we consider subordinate to stable manifolds, would be there any principal difference?
Yes, because the definition of the SRB measure, it means SRB measure lives in the unstable manifold.
Yeah, but you can take inverse mapping, and then it is, of course, measures may be different. But
we measure different.
But stable is the same as unstable if you consider F minus 1. If you consider diffeomorphism, not endomorphism.
Yes, but in case of the diffeomorphism, yeah, it should be true, but endomorphism, I don't think so.
Endomorphism, you should consider usually inverse limit, but
yes, yeah,
different story.
Yes. Okay. And okay. Let us see an example, which is a physical but not SRB measure. Bowen example. Consider a time one follow map where the Dirac point at hyperbolic fixed point of the P is a physical measure because the basin contains everything except these 2 points, Q1 and Q2. And one can adopt this example such that P is an indifferent fixed point. Imagine you have all negative Lyapunov exponent. Negative Lyapunov exponent. So then it's not SRB measure. So that was the example of the physical measure, which is not SRB measure. This example is called a Bonatti example. So to sum up till here, what we know that about the system, very basic system, that physical and SRB measure might not exist, but observable measure are exist. Let's discuss of the existence of the SRB measure. Assume that F is a C1 plus alpha and the lambda is a uniformly hyperbolic attractor. There are at most finitely many ergodic SRB measure on attractor. This result was proved by Sinai for the case of the unobserved diffeomorphism. Bowen and Ruel extended the result for hyperbolic attractor, and Bowen and Ruel constructed SRB measure for unobserved. And I will explain some idea how they prove that existence of the SRB measure in following. So we know that how to construct SRB measure for uniform hyperbolic attractor. So one may ask how we can extend it for more general class of the system. So a more general than hyperbolic, uniform hyperbolic is partial hyperbolic system. So let's discuss partial hyperbolic system. And the main aim of the study consists to understand how property of the uniform hyperbolic system extends. Let's define partial hyperbolic system. I mean, all definition I consider partial hyperbolic system for whole manifold, but everything's worked if you restrict it to some attractor or some invariant compact set. Let F be the C1 diffeomorphism compact Riemannian manifold. We say that F is a partial hyperbolic if there exists a continuous DF invariant splitting. Tm, we satisfy there are constants c greater 0 and the lambda between 0 and 1, such that for any x belong to manifold, norm of the derivative of f power n restricted to central stable direction is smaller or equal than c lambda power n, co-norm of the derivative f power n restricted to central and stable direction for all n positive, and m is a co-norm, and that's the definition of the co-norm. So that's the definition of the partially hyperbolic system. Now I would like to discuss the result for existence of the SRB measure for partially hyperbolic system. Now, and let me mention, I will write ES and EU instead of the ECS and ECU if they have a uniform behavior in this talk. I forgot to mention.
Do you allow one of these spaces zero-dimensional? Just
No.
At least one-dimensional each. CS and
yes,
CU.
exactly.
Okay.
Okay, now I'm going to discuss partial hyperbolic case. In this case, you have a uniform expanding, and you have a central stable direction. So I'm going to discuss of a partial hyperbolic system in this case. You have a uniform expanding and plus central stable cases. Before I mentioned at Pessin-Sinai result, let me define Gibbs-U measure. We say that mu is a Gibbs-U measure for a partial hyperbolic diffeomorphism if the conditional measure of the F invariant measure mu on a strong unstable plug are absolutely continuity with respect to Lebesgue restricted to unstable disk. That's the definition of the Gibbs-U measure. The reason it's called a Gibbs-U measure because considering case of the uniform hyperbolic cases or unstable diffeomorphism, a Gibbs measure for a potential minus log derivative of the function restricted to unstable direction is a Gibbs measure, and this Gibbs measure in fact is a SRB measure. That's the reason it's called a Gibbs-U measure. But here I'm talking about the partial hyperbolic system. So we have a Pessin-Sinai result again for these cases. You have a uniform expanding and plus the central stable cases, because dual case is much difficult than after this case. What I mean dual case, when you have the uniform contraction plus central unstable cases, because SRB measure basically lives in the unstable manifold. So when you have the uniform uniform expanding, then you can use after the classic technique to construct SRB measure. I will explain what I mean classic technique. The Pessin-Sinai is as follows. Let lambda be partial hyperbolic attractor for diffeomorphism of the F. Then there is some Gibbs-U state supported on attractor. The technique as follows. Since they have a uniform expanding, they can use the classic technique. What is classic technique? As follows. They consider a local unstable manifold of the gamma U, and showing that any weak star accumulation point of the sequence of the D sequence has the conditional measure on local unstable manifold, which are absolutely continuity with respect to Lebesgue. So they show that any accumulation point of the D sequence is a Gibbs-U state. So since you have a Gibbs-U state, if you have a negative Lyapunov exponent with respect to this Gibbs-U state, this implies that your measure is SRB. Your measure is SRB. And when I'm saying classic technique, I mean this technique. This technique is called push forward technique to construct SRB measure. Okay, again, I'm discussing this case, uniform expanding and plus central unstable. We consider the largest Lyapunov exponent in ECS direction. I mean, that's this lim supremum 1/n log dfn restricted to x. And that's the largest Lyapunov exponent in the direction of the ES. And we say that ECS is a mostly contracting if for any unstable manifold of the gamma U, then we have a negative Lyapunov exponent. Sorry, here it should be lambda CS. I mean, corresponding this one. For a positive Lebesgue measure set of this. Roughly speaking, I mean this. I mean we have a negative Lyapunov exponent on some positive measures. Then Bonatti Viana used the Pessin-Sinai result to show that the finiteness and uniqueness of the SRB measure. Again, these cases. Pessin-Sinai, they proved that the existence of the Gibbs US state, and this result is about of the uniqueness and finiteness of the measure of the SRB. And they used, I mean, the technique, I mean, the use of the result of the Pessin-Sinai, this result. To more precise, let F be the C1 plus diffeomorphism on a compact Riemannian manifold that admit dominating splitting again. We have a uniform expanding plus ECS is mostly contracting. It means you have a negative Lyapunov exponent in the direction ECS. Then there are ergodic SRB measure mu1 till mu(n) supported M, and if the leaves of the unstable foliation are dense, then there is a unique SRB mesh.
Sorry, what is n here? Just a finite number or some dimension?
Yes. I just want some finite number. N is I mean the yes. Are there any questions till here? Okay, let's discuss dual case, which is much difficult than of the list. Again, the reason is difficult because here you don't have a uniform expanding, you just have a uniform contraction. Let F be the C1 plus diffeomorphism on compact Riemannian manifold that admit dominating splitting like this. There exists a set of the H of the positive Lebesgue measure on which F is a non-uniformly expanding along ECU if there exists a constant lambda greater 0 such that for all x belong to H, we have a this inequality. What this inequality means? Okay, forget whatever is the before of the logarithm. Just consider logarithm of the norm inverse of the these restricted to ECU FGX. What does it mean? If you forget whatever is the behind of the logarithm, that's the definition of the uniformly expanding, because there exists a constant, I mean positive constant, and then when you take it inverse, it should be negative. I mean uniform constant, which the log of the norm is always smaller. That's the definition of the uniformly expanding. But what non-uniformly expanding, they say that take an average of these things, because that's the idea. Because okay, they cannot work with the general things. They want to use of the something close to uniform hyperbolic case. That is why they introduced such a condition. Then Alves, Bonatti, Viana, they show that in this case again, you have a uniform contraction. Assume that F is a non-uniformly expanding along ECU, then the set H is contained in union of the basing finitely many SRB measure up to 0 Lebesgue measures. This result some years ago improved by this guy, Alves, Diaz, Lozata, and Pinheiro. What they did, they replaced this lim subcondition by lim inf. they replace the lim2 by lim. Okay, that's the main result of this paper by Alves, Bonatti, Viana. Yeah, they show that there exists finite SRB measure for this system under non-uniformly expanding along ECU. They also have another result, which is mentioned in section 6 of the their paper. They prove that for general partial hyperbolic system, in these cases, you don't have a uniform contraction. For general partial hyperbolic system, for partial hyperbolic system with ECU non-uniformly expanding, imagine you have a general partial hyperbolic system with assumption ECU is a non-uniformly expanding. They prove that diffeomorphism admits an ergodic Gibbs U state. So for general partial hyperbolic system, if you have a non-uniformly expanding, there exists Gibbs U state. So if the Lyapunov exponent of this Gibbs U state is negative, the measure is SRB. That is why they ask this question. Alves, Bonatti, Viana, they ask this question. They ask whether the result is true. If the non-uniformly expanding condition replaced by Lyapunov exponent, largest Lyapunov exponent, the inverse, restricted to ECU, which means that positively all Lyapunov exponent in the center are on a stable direction. They ask this question. Basically, if one gives the positive answer to this question, it means that they give a positive answer to Viana conjecture for partial hyperbolic system because of this result. Because if one prove that, this condition, Lyapunov exponent implies, for instance, non-uniformly hyperbolic expanding along ECU, then there exists Gibbs U state. Since Viana conjecture, they say that you have a non-zero Lyapunov exponent, the Lyapunov exponent in ECS direction is the negative, so this implies that exists an SRB mesh. So to be more precise, I mentioned that the conjecture for partial hyperbolic system, that's a Viana conjecture for partial hyperbolic system. Let F be in the severus diffeomorphism on compact Riemannian manifold that admit the dominating splitting. If Lebesgue almost every X that satisfy, the Viana conjecture stated we have a non-zero Lyapunov exponent. In case of the partial hyperbolic system, it means that largest Lyapunov exponent in ECS direction is a negative, which is written here. And a smallest Lyapunov exponent in ECU direction is positive. So when you take an inverse, it should be negative. So that's a Viana conjecture for partial hyperbolic system. Then F has a physical SRB measure. So till here, are there any question or comment? Okay, now I'm going to mention assumption of the main theorem. One of the things that was used is the technique of the Lyapunov maximizing observable mesh. Let T be the homeomorphism map on compact manifold X. Assume that A is a matrix cocycle, and let mu be T invariant measure, and we denote Lyapunov exponent of this lim 1/n integral log norm A in X d mu X as n goes to infinity. An observable measure of the mu, we know that observable measure always exists, is called the Lyapunov maximizing observable measure for a cocycle A if the Lyapunov exponent of with respect to this invariant measure equal to supremum of the Lyapunov exponent over the space of the observable measure. But this supremum is always attained. It means that the Lyapunov maximizing observable measure exists. The reason is that this supremum attained because the Lyapunov exponent measure is upper semi-continuous with respect to weak star topology, and the set of the observable measure O is a weak star compact, so the supremum is always attained. So we know that this measure, Lyapunov maximizing observable measure, always exists. Let T be a homeomorphism. Assume that A is a matrix cocycle. We say that Lyapunov spectrum of the cocycle AT has a uniform one gap property if there exists a C0 neighborhood of the UA of the cocycle. Consider a neighborhood around of the cocycle A and constant beta D such that for every cocycle B which belongs to this neighborhood, we have a this. Difference between of the first and the second Lyapunov exponent is the greater to beta. It means that we have always uniform gap between first and second Lyapunov exponent. But for all cocycle which is belong to neighborhood. Again, pay attention. I'm not talking about of the all neighborhood. I'm just saying if there exists at least one neighborhood is enough. So now I can mention the main result. Let F from M to M be the C1 diffeomorphism on compact Riemannian manifold that had been dominating in split. General partial hyperbolic system. Assume that Lyapunov spectrum of the cocycle. Pay attention to this cocycle. What is this cocycle? I consider derivative of the I take inverse, then take a derivative restricted to ECU direction. Then I'm saying that this cocycle has a uniform one gap property with respect to Lyapunov maximizing observable measure. So this is a cocycle. So for this cocycle, there exists Lyapunov maximizing observable measure, as I explained. This measure always exists. Unlike physical measure or SRB measure, this measure always exists. But I just assume that Lyapunov exponent, first and second, there is a uniform gap between first and second Lyapunov exponent. Just uniform gap between first and second. Then I give an affirmative answer to Alves Bonatti Viana question. If the Lebesgue almost every x satisfy this, lim supremum 1 over n log norm inverse of the DFN restricted to EC smaller than 0, then this implies that non-uniformly expanding along ECU direction. And this assumption, a uniform one gap property, again, it's also close to Viana conjecture because Viana conjecture to say that if we have a non-zero Lyapunov exponent, here I'm not discussing whether there are, maybe the gap, one of them, there's a gap between first and second Lyapunov exponent. Maybe second Lyapunov exponent is a 0 or first one is a 0. Yeah, I'm not discussing about the positiveness of the Lyapunov exponent. I'm just saying that there is a gap between first and second. Then we have this situation for many systems. Then I'm saying that this gives a positive answer to Alves Bonatti question. So as a corollary, we prove that Viana conjecture for partial hyperbolic system for C1 plus alpha. And pay attention here, this result is for C1. So we prove Viana conjecture for C1 plus alpha. let F be the C1 plus alpha diffeomorphism on compact Riemannian manifold that admit dominating splitting. Assume that Lyapunov spectrum of the co-cycle of the inverse of the DF restricted to ECU has a uniform gap property with respect to a Lyapunov maximizing observable measure. If Lebesgue almost every X that satisfy, I mean, if you have a non-zero Lyapunov exponent, as Viana suggested, then F has a physical SRB measure. Which is the Viana conjecture for partial hyperbolic system. And the proof, I mean, this proof of the this corollary is easy, as I explained before, because by my main theorem, we know that F is a non-uniformly expanding along ECU. So Alves, Bonatti, Viana, they show that F has an ergodic gives you a state. Since I assume that mostly contracting, what I mean mostly contract, I mean this assumption. Mostly contract, I mean this assumption. Imply that the Lyapunov exponent of the mu is a negative, then Pessin theory imply that mu is a physical SRB measure.
Do you assume this split, this dominated splitting is on the whole manifold?
Yes, yes, but it also works. I mean, if you restrict it to some attractor, I mean, I haven't written carefully, but it works. If you have some attractor restricted to attractor, everything works for attractor. Here, I mean, I was so lazy.
Yeah,
I just.
But then you restrict everything to this invariant subset. Yes.
Exactly. We need to restrict everything to this invariant thing. But I mean, I was lazy. I just write it for whole
manifold.
manifold.
I have the right intuition that all this is about invariant cones. If we have such special unstable, which is there is this gap, then if you start with, say, yeah, somehow forward invariant cones would work if you take even foliation not into the right unstable, then you take images, then angle with the limit unstable foliation shrinks, and in the limit you obtain something nice along unstable. Am I right that the main arguments are about the forward invariant cones here?
No, I haven't used it after the forward invariant cone, but I mean, somehow, I mean, the answering of your question is also a bit related to forward invariant cone. Okay, let me explain. The reason I assume that this uniform one gap property, because I need some kind of a bit domination or existence, as you mentioned, uniform cone field on the support of this measure. So I need domination, not everywhere, just support of this measure. I want to have some kind of domination on the support of this. For making, I mean, to have this domination, one needs to assume that uniform one gap property. But I mean, if you are asking, I mean, directly use of the cone field, no, I haven't used of the cone field technique here. So let us see some things about of the proof. There are, I mean, some idea of the proof. The main idea I used something is called ergodic optimization of the Lyapunov exponent. Let me remind what is ergodic optimization of the Lyapunov exponent. By key-max-additive ergodic theorem, we know that for any mu belongs to a space of the t-invariant Borel probability measure, and mu almost every x such that positive part of the norm is integrable, then top Lyapunov exponent exists. I mean, this lim 1 over n log norm in x as n goes to infinity exists. So one may ask about the supremum value of these things. So we define the maximal Lyapunov exponent, I mean beta a, which is lim 1 over n log supremum of the norm x over compact metric space of the x. And that's equal to supremum of the Lyapunov exponent measure over the space of the t-invariant Borel probability measure. Since the Lyapunov exponent measure is an upper semi-continuous and the space of the thin variant Borel probability measure is a compact and convex with respect to weak star topology, supremum is always attained, and such a measure will be called a Lyapunov maximizing measure. I mean, in ergodic optimization of the Lyapunov exponent, we have a main question. I mean, the main question is as follows. Say the entropy of the Lyapunov maximizing measure is 0 under generic assumption. I mean, this conjecture. For typical kinetic system xt and typical smooth function f, the maximizing measure is unique and has a low complexity. And this conjecture, in case of the Birkhoff averages, was proved by Gonzalez and Torres. So if xt is an expanding map, then generic Lipschitz function, even though it works for Holder, has a unique maximizing measure, which is supported on periodic orbit. And now we have this question that says, is the conjecture true for Lyapunov exponent? I mean, the entropy of the Lyapunov maximizing measure is 0 under generic assumption. And recently, with the Philippe, we give a positive answer. I mean, we prove Contreras theorem for matrix co-cycle. But in general, we have a famous result of the Bush and Mireis. Give a contour example of pair of the matrices in GL2 such that maximizing measure are Sturmian, but not periodic. So we have this result. So now what I want to do, I want to study ergodic optimization of the Lyapunov exponent over the space of the observable mesh. I mean, general ergodic optimization want a study over the space of the whole space of the thin variant Borel probability measure. Now I want to replace it by a space of the observable measure, by a space of the observable. What happened? Oh, yes. Let phi be the subadditive potential, then essential supremum of the limb supremum 1 over n log phi n x always is smaller or equal than supremum of the Lyapunov exponent measure over the space of the observable measure, and that's smaller or equal than limb supremum 1 over n essential supremum of the log phi n, where essential supremum taken against of the Lebesgue. So in ergodic optimization, instead of the essential supremum, we have a supremum. Everywhere we have a supremum. But here we have an essential supremum. Moreover, these things, because I mean essential supremum, it is you can have full Lebesgue measure set, and full Lebesgue measure set is a dense. So this is the maximal Lyapunov exponent. That's the maximal Lyapunov exponent. Let us see a nice corollary of the previous theorem. Let F be the C-infinity map on compact smooth manifold M to itself. Then topological entropy of the C-infinity smooth system as follows: lim 1 over n log integral of the max norm of the wedge product of the derivative of Fn at point x d Lebesgue x as n goes to infinity. This result was proven, I mean, one side was proven by Felix for C1 plus alpha. I mean, this side was proven by Felix. Then you made finish it. I mean, the prove the other side. And Kozlowski use of the Eumedian idea to give a nice, I mean, construction of things. So one can use of the previous theorem to prove this nice corollary. Assume that F is a C-infinity map on a compact smooth manifold M, then topological entropy of the F is greater or equal than essential supremum, lim supremum 1 over n log maximum of the norm wedge product of the K dx Fn as n goes to infinity. again, essential supremum is taken of the Lebesgue measure. Again, take a look. I mean, this color is somehow surprising things because we know the role in inequality, and role inequality say that, I mean, for C1 plus alpha or C1, entropy of the map, entropy of some, I mean, invariant measure is always smaller equal than the positive Lyapunov exponent. But this color already says something, I mean, somehow is the opposite of the role inequality. Then we have this question by David Bouquet, which is close to this quarrel. David asked, do we have a supremum of the major theoretical entropy over the space of the observable measure, a smaller equal than essential supremum, the lim supremum 1 over n log norm of the d derivative of the n at point x for C1, I mean, or C1 plus alpha surface diffeomorphism. Because I mean, for more than dimension 2 is not true question. They just ask for surface diffeomorphism. Again, supremum is over the space of the observable measure.
The formulation by Newhouse, he considers not integral like I consider it,
yes,
Youngin, but kind of that for every hypersurface, the growth is smaller than topological entropy.
Yeah.
So your corollary would be something related to Newhouse formulation.
Exactly. Exactly. Yeah, exactly. So let us back to main theorem. So that's the main theorem of the paper, which I proved that, I mean, we have in fact equality here. I mean, previous theorem they say that, I mean 2.3 and one side of the 2.2 follows from previous theorem, which in previous theorem I don't assume anything. But for equality, I mean this equality, I need a one uniform gap property, uniform one gap property. So for this equality here, I need a one uniform. I mean, one side is follow, I mean, from previous theorem, which I don't assume anything. But for proving other side, I need the one uniform gap property. I also asked this question in my paper, whether one can remove a one uniform gap property. But my intuition is, I mean, it's difficult to remove it. I might be wrong, but I don't think so. Again, I mean, essential supremum again taken against of the Lebesgue measure everywhere. So that was I mean, the main theorem of the paper, which helps to prove Viana conjecture. I'm not going to discuss of the proof this theorem, which is so technical, but I just want to mention that's the main reason. And one can compare this result by ergodic optimization of the Lyapunov exponent. Just replace the essential supremum by supremum. And again, this is a maximal Lyapunov exponent. And let me mention the inequality. This inequality, you see, could be strict. And as we expected, because that's a maximal Lyapunov exponent. So let us see an example in which this inequality is restrict. The unique SRB measure mu is a unique observable measure for any transitive C1 plus alpha honors of diffeomorphism. That's obvious by definition. But there are infinitely many ergodic measures which are not observable. I mean, consider those points supported on periodic orbit. So there exists a continuous real value function phi such that supremum of the Lyapunov exponent over the space of the observable measure is smaller than lim supremum of the 1 over n essential supremum phi nx. Phi nx is a Birkhoff sum. again, this value, this is maximal Lyapunov exponent.
It's maximal Berkov average.
Maximal Berkov averages. Yes, sorry. Maximal Berkov averages. One of these periodic orbit, which are not observable measure, C be an ergodic measure, which is not observable measure. This example. Then we have this result by Jenkinson. Jenkinson said, let mu be any ergodic invariant Borel probability measure on X. Then there exists a continuous function f such that mu is a unique f maximizing measure. So the proof follow from the Jenkinson result. We can find some continuous function f for this measure such that Dirac of that point C is a unique maximizing measure. So that was the example. We show that 2.3 could be restricted. Now we have a Tian result. Tian have this result. They say that let T be the topological dynamical system on compact metric space X. Assume that AN and BN are two subadditive sequence. What I mean subadditive, AN plus K is smaller equal than AN TKX plus AK, and BN plus KX is smaller equal BN TKX plus BK. And ANX is smaller equal than AN plus X plus BKTX. If lim 1 over n, Lyapunov exponent AN for every observable measure, is negative, then we have a non-uniform expand. Again, you need three things: subadditivity of the two sequence AN and BN, and you have a negative Lyapunov exponent for all observable measure. All of them. Then you have a non-uniform expand, as you see. So the proof of the main result, what I mean main result, let me remind you main result. This result. Now I'm going to explain how to prove this result. For C1 diffeomorphism, dominating splitting, and one uniform gap, then negative Lyapunov exponent imply the non-uniform expand. Now I'm going to discuss, proof of this theorem. Okay, let A be the derivative of the inverse f restricted to ECU. Then by my theorem, essential supremum of the Lyapunov exponent is equal to supremum of the Lyapunov exponent over the space of the observable measure. We assume that essential supremum is equivalent to say that for almost every point the Lyapunov exponent is a negative. So it implies that this is a negative. Then consider AN log of the derivative of the f power minus n restricted to ECU, and Bn log dfn restricted to ECU. Both they satisfy the Tian condition. Moreover, we have a negative Lyapunov exponent for all observable measure. Then the result from Tian theorem. So the main point was to prove that relation between the positive Lebesgue measure set and observable measure. This result. Are there any questions? Okay, great, it's clear. Now we have another code. Let F be the C1 diffeomorphism on a compact Riemannian manifold that admit the dominating splitting, where ES again is uniformly contracted. Again, ECU and ES. Assume that the Lyapunov spectrum of cocycle has a uniform one-gap property with respect to Lyapunov maximizing measure mu. If we have a negative Lyapunov exponent in the, for inverse of map in direction ECU, then we have this result. Set of the observable measure equal to set of the physical measure and equal to set of the SRB measure for this system. One side is clear. Any SRB measure is physical, follow from pacing theory. Any physical measure is observable, follow from definition. Now, but this already says that they are equal. And this gives a nice construction for this system that we know that, in fact, observable measure are all SRB measure. So for proof of this corollary, I need to mention something about observable measure. Again, the set of the beam, basin of the attraction, as I define it. Oh, sorry. This one is a PW. It's basin of the attraction. And inspired by this definition, we define basin on the attraction of the space of the observable measure, which is set of the X, where PWX is a subset of the observable measure. PWX is a set of the accumulation point of the empirical probabilities. Then categorize and inherit to prove that O and the space of the observable measure is smallest weak star compact containing for Lebesgue almost all initial state. The limit of the all convergent subsequence of the empirical measure. What does mean this theorem? What theorem to say? The theorem to say that O equal to intersection of the all K, where K belongs to W, where W is a set of the K, which is set of the compact set, subset of the space of the Borel probability, such that the Lebesgue of the GK is a 1. So O is a smallest weak star compact. So by using of this result, one can prove that previous corollary. How one can prove that? Okay, we know that by the theorem, in case of the, when you have a uniform contracting, yeah, Alves, Bonatti, Viana, they show that there exists finite SRB measure. There exists finite ergodic hyperbolic SRB measure for Fk. And union, their basis form a set of the Lebesgue full measure. Okay, we write this SRB measure, that finite till mu k. Now we define new I, new measure, which is form of the somehow empirical probability. 1 over k mu I b plus mu I inverse b till mu I f minus k for any Borel probability measure. And it's obvious that Vi is ergodic, hyperbolic, and SRB. But as I wrote it, form of the compact set of the O. And the union, as I mentioned, basin of the V form set of the Lebesgue full measure. But the categories inherit, they prove that O is the smallest. So O is coincide with this finite Vi. So I think that was the last slide. And thank you very much for your attention.
Thank you. Are there questions, comments? Could you maybe show once again this Tian result? It was, I think, page 35 or around. Yes. What is the meaning of the assumption? I mean, we have the subadditive potential A. We have
Yes.
some superadditive potential minus B.
No, we have a subadditivity of the A and the B.
Yes, so it means minus B is superadditive.
Yeah.
And we have this formula 2.5, which
Yeah.
when we compare it with the 2.4, it says basically that A can be somehow bounded by B.
Yes, roughly speaking, I mean, this formula, I want to show that the relation between a function and inverse of the function. B, I mean,
B doesn't appear any further. It is the condition for A.
No, it's up here. I mean, I show you. Look at, consider A this and B this.
No, I know how you use this. But I mean,
yeah. I mean, in general, no, we don't need and that's your point.
Theorem of Tian. This is the working thing is A, and the existence of B is the assumption on A.
Yes, exactly. Yeah, we don't need B in, I mean, essentially. Yeah, that's in general, A play important role.
But there's also no condition like integrability on B, or
no.
Well, I guess subadditivity implies everything, every integrability.
Yeah, but integrability, because here I'm talking about of the topological dynamical system, compact metric space, then you have some kind of integrability, I think.
Because A and B are continuous, yeah? So
yes.
Okay, yeah, I'll continue.
Okay, well, it's interesting. I don't understand it at the moment, but maybe someday I will. Okay, any questions? Okay, so let's thank the speaker.
Thank you.
You're welcome.